Digital logic circuits are classified as combinational circuit, sequential circuit. Combination circuit examples are comparator, half adder, full adder, half subtractor, full subtractor, multiplexer, demultiplexer, encoder, decoder. Whereas sequential circuit examples are flip flop, counter, register, half adder. Half adder means sum s equal to a bar plus b plus ab bar, then about a xor b, carry c equal to ab. Whereas total number of NAND gates required to implement half adder equal to 5. Total number of NOR gates required to implement half adder equal to 5. To implement the half adder circuit by minimum number of logic gates, if we have all gates except XOR and XNOR is 3. Total number of 2 is to 1 mux required to implement half adder equal to 3. Full adder, it performs arithmetic sum of 3 input bits, that is addend bit, augment bit and carry bit. Augment bit logical expression sum s equal to a xor b xor c, carry c equal to ab plus bc plus ca, that equal to ab plus c into a xor b. See, sum equal to s equal to xor b plus xor c, where carry c equal to ab plus bc plus ca, that equal to ab plus c a xor b. Remember, a full adder can be implemented by two half adders and one OR gate. Two total number of NAND gates or NOR gate required to implement a full adder is equal to 9. 9 కావాలి. Total number of 2 is to 1 mux required to implement full adder equal to 7. Half subtractor, logical circuit, logical expression, difference d equal to a bar b plus ab bar equal to a xor b, borrow b naught equal to a bar b. Total number of NAND and NOR gates required to implement the half subtractor is equal to 5. Total number of 2 is to 1 mux required to implement half subtractor is equal to 2. Equal to 2. Full subtractor, it is a circuit which performs subtraction between two bits, taking into account that one may have been borrowed by a lower significant stage. Logical expression difference d equal to a xor b xor c, borrow b naught equal to a bar b plus a bar c plus bc are equal to a bar b plus a xor b whole bar into c. A full subtractor can be implemented with two half subtractors and one OR gate. Number of NAND or NOR gates required to implement the full subtractor is equal to 9. In parallel adder, n full adder or n minus 1 full adder and 1 half adder or 2 n minus 1 half adder and n minus 1 OR gates are required to add two n numbers. Total number of 2 is to 1 mux required to implement full subtractor equal to 7. Look ahead carry adder, it makes the addition faster. It is based on the two additional signals that must be computed. Generator signal Gi equal to AiBi, propagation signal Pi equal to Ai XOR Bi, the carrier signal generated Ci plus 1 equal to Pi Ci plus Gi. Number of AND gates required in carry circuit for n bit adder is capital N equal to n into n plus 1 by 2. Number of OR gates required in carry circuit of n bit adder is n equal to small n. Non-arithmetic circuits. Multiplexer is a combinational circuit which have many data input and single output depending on selector control input. One of the input line is transferred to the output, hence it is known as many-to-one circuit or universal logic circuit or data selector circuit. The selection of a particular input line is controlled by a set of select lines. There are 2 power input n input lines where n is the number of select lines, 4 is to 1 mux. So y equal to s1 s0 into I bar I naught plus s1 bar s0 into I1 plus s1 s0 bar I2 plus s1 s0 I3. Like that, you have to remember the size of the mux is specified by the 2 power n of the input lines and the single output line. Mux contains AND gate followed by an OR gate. Mux higher order mux using lower order mux. Given mux 2 is to 1 to be implemented mux 4 is to 1, required number of mux 3. Given mux 4 is to 1 to be implemented mux 16 is to 1, required number of mux 4 plus 1 equal to 5. Given mux 4 is to 1 to be implemented mux 64 is to 1, required number of mux 6 equal 16 plus 4 plus 1 equal 21. Given mux 8 is to 1 to be implemented mux 64 is to 1, required number of mux equal to 8 plus 1 equal to 9. Given mux 8 is to 1 to be implemented mux 256 is to 1, 32 plus 4 plus 1 equal 37. To implement 2 power n is to 1 mux by using 2 is to 1 mux, the total number of 2 is to 1 mux required is 2 power n minus 1. Mux is a universal logic gate Using 1 2 power n is to 1 mux, all n variable logic functions can be implemented. Some n plus 1 variable logical functions can be implemented. Using 1 2 power n is to 1 mux and 1 NOT gate, all n plus 1 variable logical functions can be implemented. Demultiplexer. It receives information on a single line and transmits it on one of 2 power n possible output lines. Other name of demultiplexer are one-to-many circuit or data distributed circuit. Number of select lines in log n base 2 is log n base 2. Number of select line is log n base 2 where n is number of output lines. Given dmux 1 is to 2 to be implemented mux 1 is to 4, required number of mux equal to 1 plus 2 equal to 3. Given dmux 1 is to 2 to implemented mux 1 is to 8, required number of mux equal to 1 plus 2 plus 4 equal to 7. Given dmux 1 is to 2 to be implemented mux 1 is to 16, required number of mux 1 plus 2 plus 4 plus 8 equal to 15. Given dmux 1 is to 2 to be implemented mux 1 is to 64, required number of mux equal to 1 plus 2 plus 4 plus 8 plus 16. Once again, I will repeat. Given dmux 1 is to 2 to be implemented mux 1 is to 64, required number of mux equal to 1 plus 2 plus 4 plus 8 plus 16 plus 32, that equal to 63. Given dmux 1 is to 4 to implement mux 1 is to 16, required number of mux equal to 1 plus 4 equal to 5. Decoder is a combination circuit that is used to convert binary to other codes such as binary to octal, binary to decimal, binary to hexadecimal. Decoder, depending upon binary data uploaded, one of the output will become logic. A decoder has many inputs and many output lines. It is a combination circuit that converts binary information from n input lines to a maximum 2 power n unique output lines. If the n-bit decoded information has unused or don't care combinations, the decoder output will have less than 2 power n outputs. Total number of output lines m less than or equal to 2 power n, where n is the total number of input lines. Decoder 2 by 4 decoder may act as like 1 is to 4 demux and vice versa. Decoder and demux circuits are almost same. Decoder contains AND gates or NAND gates. Sequential circuits. Flip-flop is a basic memory element. It can store one bit of information. A flip-flop has two outputs which are always complementary to each other. A flip-flop has two stable states, hence it is known as bistable multivibrator. A simplest form of flip-flop is called latch. It can be constructed with two cross-coupled NAND gates or NOR gates. Triggering is used to initiate the operation of latches or flip-flops. Level trigger. Input signal affects the flip-flop only when the clock is a logic 1 or logic 0. Edge trigger. Input signal affects the flip-flop only if they are present at the positive or negative going edge of the clock pulse. Setup time. It is minimum time required to keep input at proper level before applying clock. Hold time is the minimum time required to keep the input at same level after applying clock. If setup time and hold time is not properly given, the output may go to metastable state. Clock SR, SN, clock 0, SN RX, don't care, QN plus 1 is QN. Clock 1, SN RN 00, QN, SN RN 01, 0, SN RN 10 means 1, 11 means invalid. Here 00 means QN is called hold state, 01 is nothing but reset state, 10 is nothing but one set state, 11 is a forbidden state. Sn and Rn denote the input and Qn the output during the bit time n. Qn plus 1 denotes the output Q after clock passes, that is bit time n plus 1. The characteristic equation equal to Qn plus 1 equal to S plus R bar Qn. S plus R bar Qn. Disadvantage of SR flip-flop is invalid state will be present when both inputs are 1 or high. To avoid this, JK flip-flop is used. JK flip-flop is called universal flip-flop because of the flip-flops like D flip-flops, SR flip-flops and Q flip-flops can be derived from it. S equal to JQ bar, R equal to KQ. So here 00 hold state, QN 010 reset state, 101 set state, 11 QN bar, that is called toggle state. Characteristic table QN plus 1 equal to JQN bar plus K bar QN. Race around condition. The race around condition will occur when J equal K equal to 1. TPD of flip flop is less than TPW. Flip flop is level triggered. For the duration TPW of the click clock pulse, the output Q will oscillate back and forth between 0 and 1. At the end of the clock pulse, the value of Q is uncertain. The situation is referred as race around condition. To avoid the condition, TPW is less than TPD. Flip flop is less than T. Race around condition does not occur in edge triggered flip flops. Remember. Master slave flip flop JK flip flop to avoid race around condition. Master slave flip flop is used. Master slave flip flop. Master is applied with input clock and slave is applied with the inverter clock. Due to this, when master output is changing, slave output remains in previous state. In master slave flip flop, output will change only when slave output changes. Output of master can change many times, but slave output can change only one time. So master flip flop act as a level triggered and slave flip flop act as edge triggered. Therefore, there is no race around condition at the output of the slave. D flip flop, it is a flip flop with a delay equal to exactly one cycle of clock. J equal to D, K equal to D bar, Qn plus 1 equal to D. It is also known as transparent latch because Qn plus 1 equal to D. Toggle flip flop, T flip flop. The T flip flop is a single input version of the JK flip flop. T flip flop can be obtained from a JK flip flop if J and K are tied together as in shown figure. The destination T comes from the ability of the flip flop to toggle or change state. Truth table qn plus 1 equal to t bar qn plus t qn bar are nothing but t xr qn. Conversion of flip flops: s equal to jqn bar and r equal to kqn. SR flip flop to other flip flops, that is the s equal to jqn bar and r equal to kqn. JK flip flop to other flip flops, j equal to s and k equal to r. D flip flop to other flip flops, d equal to s bar s plus r bar qn. D flip flop to other flip flops, d equal to s plus r bar qn. T flip flop to other flip flops, t equal to s qn bar plus r qn. Whereas SR flip flop to other flip flops, S equal D and R equal to D bar. JK flip flop to other flip flops, J equal to D and K equal to D bar. D flip flop to other flip flops, D equal to JQN bar plus K bar QN. T flip flop to other flip flops, T equal to JQN bar plus KQN. SR flip flop to other flip flops, S equal to TQN bar and R equal to TQN. JK flip flop to other flip flops, J equal to K equal to T. D flip flop to other flip flops, D equal to TXR QN. T flip flop to other flip flops, T equal to DXR QN.